situation in which you could send 1,000 packets to the same destination, and theoretically, each of the 1,000 packets could take a different destination, a different route to the destination. Okay? Yeah, and it'll work something like this, and this is the example I used on last night's class. The highways that we use to get from point A to point B are similar to the links or interfaces connected to a router. Now, when it's time for me to go home, and I get in my car, get on this somewhat of a service road that's out here, that's like me getting on one of those interfaces, right? When I get to a stop sign or a stoplight, that's inside of another router with different interfaces leading to multiple directions. Which route do I take? Well, generally I take a specific route home. But if I notice on this particular day that there's congestion, traffic is backed up, then I have the option of, hopefully I have the option of taking an alternate route. Routers do the same thing with information. If a router has a specific route that it would, or a specific path it would send a packet, but however on this particular instance that path is congested, it may switch that packet to an alternate path. And that could happen thousands of times before all the data reaches the destination. Intersections can be considered similar to the interfaces connected to a router.
Okay. How can it tell about congestion, that there's congestion on the network and that it needs to be resolved?
How can it tell about congestion? We'll get more into that in NAT 126 and maybe the end of this semester. But that's something we'll spend more time with the NAT 126. Okay. That's only for networking measures. Yeah. Okay. All right. We've seen this output before, right? We just type ipconfig, and if we want to see more details, we type ipconfig/all. Okay. All right, routers keep track of networks by building something known as the routing table. It's basically a rudimentary spreadsheet. It's just like has networks listed and then simple directions how to get to those networks. And this is an example. In order to get to network 10.1.1.0, the router knows that it needs to send the packets to this next destination. Okay. We're really looking at the routing table of this router, the local router. Okay. And if we want to get a packet to the 10.1.1.0 destination, then the local router will send that packet to the router that has the IP address 192.168.2.2. Okay. That's an interesting way of looking at it. It's sort of like an airport. Yeah, airports pretty much work the same way. You just, very rarely do you go from one location to the next without making some type of interim stop at a different airport, right?
And they have security too.
And they have security too, okay. They have firewalls. Okay. All right. Your PC also has a routing table. This is an example of a Windows PC routing table. Okay, we see the wildcard destination. Wildcard just basically means anything unknown should be given to this particular gateway. For example, if a packet is destined for 200.200.200.200, it's going to automatically be sent to the default gateway, and it's going to go out of this particular interface, which is the IP address of the PC. However, if something is destined for 192.168.1.0, which is the local area network, It's basically going to be sent to the PC itself, and the PC itself is going to send it out of its own interface. Okay, and you may note the metric column here. Metric is basically a value assigned to routes. Okay, in terms of determining which route a packet will take, the route with the lowest metric will be selected. Okay, it's sort of like what is actually like the mapping system that we use in our GPS system. Believe it or not, at some point somebody drove all those streets and put the street information into a map database. And as that somebody drove a particular street, that person assigned a value to that street, a metric. Okay, so what happens is when I decide to take a route from here to, let's say, Raleigh, and if I choose a certain route, let's say going up Greenville Boulevard and then getting on 264, well, the person that drove that route probably gave, let's say, for example, Greenville Boulevard a metric of 5 because it has stoplights. But they probably gave 264 a metric of 1, all right? So if I decide to take that route, then the overall value of that route would be a 6. Now, what if there's a way for me to get on another road that leads to 264 that has a metric of 2? Then the mapping system will automatically calculate that as being the best route because it's going to say the overall value to get to Raleigh is going to be a metric of 3. It's 2 plus 1, 1 being 264, and that other route has the value of 2. Routing systems work in a similar fashion. Okay? So metric is basically a value to determine the congestion of a route or the feasibility of a route. Okay. You know, when we shop, okay, this is another look at a routing table. We'll get more into routing tables perhaps the end of this semester, definitely in NAT 126. I'm surprised nobody's asked, well, how do routers know about other destinations?
I kind of assume that they kind of program it.
Wow, okay, Will says he assumed that the routes were programmed to the route. Yeah, routers learn about other networks via one or two methods. Someone will have to literally program those routes, and we call that static routes, or the routers can be configured to learn routes from other routers, and we call that making use of a dynamic routing protocol.
Where one router will learn about another router, if the other router is putting in a package or whatever, and the router that is here registering it.
Well, okay, what happens is once you configure the routers to use a dynamic routing protocol, and we assign those routers IP addresses, those routers will automatically advertise those IP addresses to all the other routers in that domain. Okay. Yeah. So what would be the benefit of using a dynamic routing protocol opposed to statically assigning or programming those routes in a router?
There's millions, pretty much every day, and everything is followed with the buses, so they can kind of learn from each other.
Oh yeah, yeah. Especially if you're talking about the internet. The internet consists of thousands, perhaps millions of routers. And let's say a router goes down. How long would it take to program all those other million routers to be aware that the route has changed, or the route is no longer, or the network is no longer there? Okay. But using the dynamic router protocol, you could perhaps, or routers could perhaps be informed of a change in a matter of microseconds, or nanoseconds.
When a router or something goes down, they can notify.
Exactly. Yep. Mm-hmm. Yeah, because oftentimes those routers send what's known as a keep alive. It's a little signal every so often saying, hey, I'm here. I'm awake. Are you there? And if they notice that a router is no longer sending a keep alive, they'll automatically assume that that router is down, and it'll advertise to the other routers, hey, I just lost connectivity to router X. Okay. Okay, we'll say it's sort of like a roads out. Are you watching the news and they're telling you, hey, don't take highway such and such because of construction or whatever the delay is. Exactly. Yep. What's that? Or planes down. Yeah. Yeah, that's a little more serious. Okay. So routers learn about networks via one of two ways. And what are those two ways? Static or dynamically. Okay.